This is your video for lesson 25-1. Um, First thing that I need you to do, if you have not already, is to get out your book, and I'm looking, it's on page 387, so you need to be following along. I'm pulling it up here, the same types of questions that you have in your book to go through the lesson together. So need you to be on page 387, please. So while you're turning there, you can see up here on the video, question 1, it says the whole speed of is a transformation of the parent square root function f of x equals the square root of x. So we're going to be learning some new parent functions in this unit, and the square root function is one of them. So this is our parent, and with any type of transformations, the first thing we need to do is learn how to graph our parent. So, of course, any type of graph we always talk about, you can make a t-chart, and we should be able to come up with some points to plot. Now, if we use the same points that we used with the exponentials, which would be -1, 0, and 1, we run into a little bit of a problem, because when I plug in -1 here, I end up with I, right? And I can't graph an imaginary. So I can't plot any negative x values here. I have to start at 0. So the square root of 0 is 0. The square root of 1 is 1. If I pick 2, the square root of 2, I don't know off the top of my head because it doesn't come out evenly. The next number that has a perfect square is 4. So the square root of that would be 2. So these are going to be our 3 parent pattern points that we're going to learn. So 0, 0, 1, 1, and then 4, 2. The shape of our parent graph looks kind of like a half of a sideways parabola. So this is our parent function and what it looks like. And it asks us to graph h and f on the same axes, and if we look here in the book, h of x is 1.34 times the square root of x. So that, obviously, 1.34 is a decimal. I'm not going to expect you to multiply that out and graph that by hand, so we're going to look at my graphing calculator here. So I put into my y equals the 1.34 square root of x. You can see that if you just glance at the shape, it looks the same. But if I look and press second graph and look at the table, there we can see the differences. So if I scroll here, notice that the negatives, it says error, so that's showing you the same thing. I can't put a negative number in for x there. But I do have different points, 0, 0, 1, 1.34, and 2, 1.89. So if I go back here and plot in a different color, it starts at 0, 0. It's 1, 1.34, so just a little bit above the parent graph. And then I believe we said 2, 1.89. Yep. Sorry, got so many windows open. So about right here. Again, we could continue plotting them if we want. Right now we've got a decent idea of the shape, which is all we really needed here. So as far as how the graphs compare to each other, obviously the red one, the h of x, is the transformation. It's a little bit taller, you might say, and that is because this is a vertical stretch. We've pulled on it. We've made it taller by a factor of 1.34, which should make sense because h of x had an a value in front of the parent graph, and as we've discussed so many times, a value controls vertical shrink and stretch. Part B wants us to determine the domain and range of f, my parent. Remember that we don't do set notation, so we just do inequalities and interval notation. Now it's important here to recognize that on my domain, we couldn't pick negative values. They gave us i's. So that means my domain doesn't go from negative infinity to infinity, and we can see that in the picture. It starts at 0. So an inequality formation starts at 0 and then continues on forever. So between 0 and infinity, that's inequality notation. If we're using interval notation, 0 to infinity, including the 0. The range, y values, also start at 0 and get bigger. So same thing. For my range values. Given that x represents the length of the boat, should the domain of h of x be more restricted than f of x? Can you determine the domain precisely? Explain your reasoning. So the parent graph is just a general function. It's not describing anything in real life right now. But h of x is, again, as it said in the question, it's the whole speed function. So it's representing speed as a function of, I believe, length of the boat. So yes, x is length of the boat in feet at the water line. So the domain, that's x values. X values are length. So yes, it should be more restricted. It makes sense to keep it with 0, except it doesn't make sense to have the equal to. We know that the length can't actually be 0. And we also know that there is some sort of upper limit. The reason we know, at least for the explaining part, explain your reasoning, we know that you can't have an infinite length boat. And you can't have a boat with a length of 0. The boat wouldn't actually exist. Now, we can't determine the domain precisely because we don't know what the restriction is. I'm sure that there's some sort of restriction where the boat wouldn't float anymore and where it just becomes impractical. All right, number 2, explain how you would use transformations of the parent graph, f of x, to graph g of x equals 2 times the square root of x. So very similar to our h of x, except that now it's a 2 instead of a 1.34. So think about it for a minute, write your answer there in your book, and we'll check it here. Hopefully you said that we would do a vertical stretch by a factor of 2, because that is your answer there. Number 3, consider f of x and a new g of x, the square root of 2x. Now notice there's a difference between these two g of x's. This one wants me to write it in this same format, but I can tell you it's not the same equation because the square root of 2, when 2 is underneath, is not the same as when 2 is on the outside. So this one, if we want to write it in this form, all we have to do is give them each their own symbol. So the square root of 2 times the square root of x is how we would write g of x in this particular form. Which then, if we look at B, explain how we could use transformations to graph. This is still a number in front, and that means because the square root of 2 is bigger than 1, that that's also going to be a vertical stretch. This time by a factor of radical 2. We're not going to do number 4 because we're not going to put negatives on the inside. So you can scratch that out, which means we can also scratch out number 5 because if we're not describing the graph, we're definitely not going to graph it. So you can cross those ones out. Domain and range of G, it depends on which domain and range we are talking about, but I assume they're talking about the 1 and 5, so we're going to skip that guy too. And let's move on. Before we get to number 9, in the margin, we need to write out our general parent function. And I'm sure by this point in the year you can kind of guess how it's going to look. But the general equation, so the parent function is f of x equals radical x, or square root of x. Our general function is y equals a times the square root of x minus h plus k. In some cases, although most not, we might have a b in there. And a, b, h, and k do all the same things that they always do. A controls our vertical stretch and shrink. B value, if we have one, controls horizontal stretch and shrink. H controls horizontal shift. K controls vertical shift. Now the A value also controls the fact that there will be a reflection in the x-axis if it's negative. So all the same things that we're used to. So go ahead and write down the transformations in number 9 that are present in each of those equations. So I'll give you a minute here. Go ahead and do that. Okay, so we're going to look at A. If you're still not quite finished, just hang on because I want to make sure you understand the explanations as we talk about them here. So this number in front, that's an A value, and the A value here is -1. So if A is -1, that means that there's a reflection in the x-axis. This value, the +2 underneath, is an H value. So H equals 2, and it's a +2, which means it's a left horizontal shift. So horizontal shift, left 2. Part B, this -3 is an H value. That means it's a horizontal shift to the right. So horizontal shift, right 3. Then the K value, that's a vertical shift. And because it's positive, that means it's up. So up 4. So those are the transformations that you should have here. So now we're going to sketch the graphs, it says, of each of the functions in item 9 as well as the parent function. So I'm going to go back to my parent function, which was, again, if we draw our parent pattern, we had 0, 1, 4, and then 0, 1, 2. So 0, 0, 1, 1, 4, 2. All right, so here's our parent graph. So we'll do h of x next since it's next up. So horizontal shift right 3, and then vertical shift up 4. So right 3, up 4, and just like I have on exponential, logarithmic graphs, sine, cosine. I'm going to indicate where my new origin is. So I made a little plus sign there at right 3 up 4 because that's where my starting point is going to be. Now remember, if there is no shrink or stretch, that means you're still using the parent pattern. It just means we're using it from this new point here. So from here, I go left or right 0 and up 0. So I make one right at that new origin. Then I go right 1, up 1. And then I go right 4, up 2. So here is my h of x function. You may want to label these since you probably aren't using different colors. And now finally g of x. Reflection in the x-axis, remember, means that I'm multiplying by -1 on the y column. It's flipping upside down. I do my shifting first, so left 2 it says. So new origin is going to be right here. And again, because of the reflection, I like to multiply my y coordinates by -1. If you just can remember to move down instead of up, that's perfectly fine. So left and right 0, down 0, right 1, down 1, and then right 4, down 2. So 1, 2, 3, 4, 1, 2. I think that the parent graph kind of looks a little bit like an eyebrow. So notice that here, because of the reflection, the eyebrow is upside down. So this is my g of x. And then the first one, of course, was my parent. It says to state the domain and range for each function. So for g of x, you can pick one notation. You don't have to do all three. Same thing in the homework. If it tells you to write it in all three notations, you can just pick one. That's perfectly fine. Also, you do not have to graph the parent every time in your homework, even if the directions tell you to. Because once we've graphed it once, we should know what it looks like. So here's g of x. Its domain, its x values. They start at -2 and they get bigger. So this is my domain. My range, my y values start at 0 and they're smaller. So remember when we list, it goes from smallest to largest, and so my range would look like this. For h of x, my x values don't start till 3, and then they get bigger, they go to the right. My range values, y values, start at 4 and get bigger. So starting at 4 with a bracket and getting bigger. And then obviously the domain and range of the parent hasn't changed, so we're not going to list that again. Now, I want you to look at the domain and the range and compared with the graph and compared then with my transformations. Left 2. And look what happened down here. Right 3, up 4. So using that, I want you to go ahead and try and answer to number 11. Just think, no one's going to prevent you from erasing it, but it does your brain good to try. So just think about what you think the domain and range of this function would be without graphing it. All right, I'm going to explain this using the transformations. When we look at this, we see as the transformations a horizontal shift left 5 and a vertical shift down 1. The reason why I'm writing that is because that's going to help you determine the domain and range. Shifting left 5 means that I'm going to start my domain 5 units to the left of what the parent would, which is at 0. So it goes from -5 to infinity on my domain. The range, because it shifts down 1, that means instead of starting at 0, it starts at -1 and gets bigger. All right, I think hopefully we've got the hang of that. What I want to look at here then is this example. It says the graph of the whole speed of a boat H is shown below. You also sketched this graph in item 1A. So this was the one that I showed you on the graphing calculator, and then we plotted the points. So this is the exact same graph there. So our points were 0, 0, 1, 1.34, and then 2, 1.89. So you can see those are falling on the graph. Number 16 says use the graph to estimate the hull speed of a boat that is 24 feet long at the water line. So the length is an x value. So when it gives you an x value and wants you to estimate given a graph, we just go straight up and we find the corresponding y value. The corresponding y value is about 6.5, maybe. And that's measured in knots. Then 17, use the graph to estimate the length at the waterline of a boat whose hull speed is 6 knots. So 6 knots, and we find where it touches, right here. So the length would be about 19 feet. And finally, 18, write an equation that could be solved to determine the length at the waterline of a boat with a hull speed of 6 knots. So, meaning if we had to do this algebraically, how would we do this? So, if we're trying to determine length, that means x is our variable. And we know that in the original equation, which was h of x equals 1.34 radical x, length is still staying a variable, so the radical x isn't going to change, which means I better have something to plug in for h of x, which h of x stands for hull speed, and they told me that was 6. Now, it didn't actually ask you to solve it, it just said write an equation that could be used to solve, which would be this one. Now, the one thing that I want to go over again really quickly, they gave you a graph here. So you could eyeball these answers in 16 and 17. It's been a while since we used our graphing calculator for these, but I want to show you again how to do that because you will need to be able to do that in some homework and or quiz test problems. So just reviewing real quickly, if I have the whole speed equation in here and I've got it graphed and it wants me to answer the exact same question, only it doesn't say use the graph, it just says estimate the hull speed of a boat that's 24 feet long at the water line. Of course, that one you could do algebraically if you wanted and do 1.34 times the square root of 24. That's perfectly fine. If we've already graphed it in the graphing calculator, the easy way is to go to my second trace menu, second trace, choice 1, value, and then just type in the x that I want, press enter. Why is it telling me invalid domain? Oh, because I didn't make my window big enough. So that's an even better review than I thought. Remembering that we have to have a domain as big as the number that we're plugging in. Of course, you could also scroll in the table too. It just takes a while to scroll down that far. So second trace, we'll try this again. 1, and then enter 24. And then look, our estimation is pretty spot on. Y equals 6.56. So when we said about 6.5 knots, we were very, very close. All right, there it is. So then 17, use the graph to estimate the length of at the waterline of a boat whose hull speed is 6 knots. So this is giving you a y value. So remember when we solve these ones, you actually have to go back to your y equals, and you have to type in the other y value that they gave you. So in this case, 6. Type it in, it graphs it, and then we have to find the intersection point. So again, it's been a while since we found intersections, but this is certainly something you need to know how to do for college and definitely need to know how to do in pre-calculus. So second trace, choice 5 for intersect. Then remember, we move the little cursor close to the intersection we want to find, because sometimes there's more than one. Once it's ready in place, it says first curve, and it's just asking, is this blue my first equation? Tell it yes by pressing enter. Then it asks, is the red my second equation? Tell it yes by pressing enter. Then it says, do you want me to guess? Tell it yes by pressing enter again. And then notice the actual answer is 20.09. So we were off in our estimate by about 1 foot. So certainly we were not off by much. You can see the difference is very small here when we did our intersection point. So that's how we find those exact answers. Again, make sure that you wrote down, the general form of what we see, because in your homework, you're definitely going to have to be able to describe those transformations. All right, that's it for this lesson.